This section of the course is going to deal with exponential functions. These are very important functions. They're all over math, and they're all over real life, okay, as well. So my goal is going to be to teach you what you need to know about exponential functions as it relates to trig and calculus and prepare you for that. So let's just go right into it. Let's say we have f of x equals a to the power of x. Now, before we get going anymore, I'm going to explain f of x. Up to now, all I've shown you is y equals 3x or something like that as an equation. Okay. What this means is you take a number for x, you stick it in here, and you get a number for y. This tells you the same thing. It's just another way of writing it. There's nothing magical about f of x. What it's really telling you, implied here, is that you've defined a function, and it is a function of the variable x. Here is the same thing. Y is a function of x. So you could say y is equal to f of x here. It's the same thing. These two things are the same thing. But I don't want you to get thrown off if you haven't ever seen that before. F of x just means y equals. Okay, and you just go from there. Okay. The equation I've defined here is called an exponential equation. This letter a is a constant. It could be, like an example, it could be 1, it could be 3.2, it could be -4, okay? It could be lots of things, okay? But it's just a constant, okay? And it's raised to the power of x, okay? So let me plot it for you and explain why it looks the way it looks, okay? Let's say this is a graph like this, okay? This is x, this is f of x, which is basically y in this case, okay? If f of x is equal to a to the x power, if this is 1 right here, now let me write it someplace else. This is 1 like this, then this equation is going to look like the following. It's going to start off here, it's going to climb, 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 climb. It's going to go on up to infinity. Okay? And as it goes this way, it's going to go down close to the x-axis. Okay? That is a general form. Get rid of this here. That is the general form for an exponential function. You kind of think that kind of makes sense. I mean, you know, in our everyday language, exponential means something gets bigger. It grows exponentially. In fact, exponential functions govern everything from growth of mold on a piece of toast. They multiply exponentially. To you know, your bank account, if it earns interest, that's kind of an exponential equation. So exponentials are everywhere, okay? And of course you might think bunny rabbits multiply exponentially and something like that. So you can see that as you go higher in x, this gets bigger, 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 bigger. And of course the graph goes on and on and on, and it just goes up very steeply up to infinity, okay? This is what the graph looks like if this constant a is greater than 1. Let's take an example. I'm just going to throw an example. Let's say f of x is equal to 2 to the x. Okay, that's my formula. A is greater than 1, it's equal to 2, and it's raised to the x power. So if you think about it over here, like let's say at, I don't know, 4. X is equal to 4. We've got 1, 2, 3, and here's 4. Okay, you know, there's some point on this line like that. Or that's not a line, an exponential curve like that, okay? What this means is that at this point, f of x is equal to 2 to the 4th power, because x is equal to 4, which is 2 times 2 times 2 times 2, okay? 2 times 2 times 2 times 2, and x is equal to 4, and so it's like this. At x is equal to 5, okay, here, you multiply by another 2. If x is equal to 6, you multiply by another 2. So you see, as time goes on, or as you go more and more to the right, it not only gets bigger, but it gets multiplicatively bigger, because every time you go to the right, it's multiplied again by itself. Okay, so it's multiplied again by itself. So this thing gets huge, 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 huge. Okay. Now think about it on this side of the equation. Let's think about, here's -1. Let's think -2. Okay. let's say we're interested in the point f of minus 2, which means let's evaluate this formula at minus 2. That would be 2 to the negative 2, right? Which, if you remember from your algebra, that's just 1 over 2 squared. Anytime you have a negative exponent, you just make 1 over and then make it a positive exponent, which means this is equal to 1/4. So you can see it's a small number, okay? And as you go more and more and more to the left, okay, this number is going to get bigger. So it'll be, as you go this way, it'll be 1 over 2 to the third. And then it'll be 1 over 2 to the fourth. And then 1 over 2 to the, eventually to the 59th, okay? And you can see that as you get negative, 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 since it's basically forcing it in the denominator, this denominator is going to get very big, which is going to drive the whole thing very close to 0. Eventually you're going to be out here and it's going to be extremely close to 0. So that explains this. As you're on this side of the equation, okay, your numbers are getting much, much bigger because they're multiplying, everything's multiplying by itself. And as you go this side, they're getting smaller because of this trick here, because of negative exponents. Now there's a very special point in the middle. You're going to need to memorize this. Again, I don't tell you to memorize everything, but there's a few things you're going to have to memorize. Any number, a, I'm just going to pick it like that, raised to the 0 power is by definition 1. You have to memorize that. So let me give you a few examples. 2 to the 0 is 1. Okay, so notice that that's f of 0 in our equation. If I take 0 and I plug it into my equation, I get 2 to the 0, so that's 1. That's why the graph crosses the y-axis, or the f of x axis, at 1, because of this relation here. So 2 to the 0 is 1, 3 to the 0 is 1, negative 2 to the 0 is 1, 3/4 all to the 0 power is 1. I'm trying to write a lot of examples to show you that no matter how you slice it, anything raised to the 0 power is 1. That is something you will need to memorize. So you can summarize it by just looking at this and say a, which is just any number, raise it to the 0 power, it equals 1. So look at this equation, burn it in your head. This is what an exponential looks like when a is greater than 1. Okay? So I'm going to go ahead and truncate this graph here. I'm going to write up here, a is greater than 1. And I'm going to draw a dotted line here. And we're going to draw a different graph, but very similar over here. Again, we're going to say f of x is a to the x, same equation. The only difference is we're going to say a is between 0 and 1. This means a is greater than 0, a is also less than 1. So it lies between 0 and 1. What this means is that a could be, for instance, between 0 and 1, any decimal point between 0 and 1, like a could be 1/2, for instance. Okay. So let's look at what the graph looks like here. Okay. You got this. Again, you got a couple tick marks to the negative side. Here's 1 again. And then you go on like this. Again, I'm just going to show you how the graph looks and draw it for you, and then we'll talk about it. This graph is going to look like this. It's kind of a mirror image of the previous graph. Okay? The exact shape of it is going to depend on exactly what a is, but the actual kind of general shape is going to be like this. This is pretty easy to verify if you think about it. Okay? If, let's say a is very big, okay? I mean x, let's say we're going, in terms of x, we're going to the right-hand side of the equation here, okay? And it's getting very, very large, okay? Well then, what I'm going to have is, since it's a to the x power, if x is like 3, I'm going to have 1/2 times 1/2 times 1/2, because I'm going to have 1/2 to the third power here. You can see that it's 1/2 times a half times a half. It's going to get smaller and smaller and smaller, because every time I'm multiplying, I'm cutting it in half every single time. Eventually, it's going to just get very close to 0. So that's what's happening there, okay? As I go negative, what I'm going to have, for instance, would be 1/2 to the to the negative 1, to the negative 2, to the negative 3, to the negative 4. So let's say I had negative 3 out here, just to compare it. We did positive 3 and we got a very small number, so let's see what happens if we go to negative 3. Well, if you remember, like we said, anything with a negative exponent, you can write it as 1 over 1/2 to the third, like that. Okay, and then this is just 1 over 8. Okay, if you just look at the bottom, 1/2 to the third power, 1 to the third power is 1, 2 to the third power, 2 times 2 is 4, times 2 is 8. Okay, so this 1 over 8, you just flip that bottom fraction over and you get 8. So that's why it's a mirror image of each other, and it's because this number is between 0 and 1. As you go negative, when the a is between 0 and 1, you get this, you get some bigger numbers. When you go positive, you get very small numbers. So this, in general, is what these equations really look like. So we're going to just do some qualitative graphing, just to kind of drive it home. What if I had f of x equals 4 to the power of x? Okay, I'm just doing qualitative graphing here. What would this equation look like? We've already talked about it a little bit. Well, you're going to have x, you're going to have f of x, you're going to have 1 somewhere up here, okay? And since it's a positive number greater than 0, you're going to have an equation that looks something like that, okay? What if you had f of x equals 10 to the x, a bigger number raised to the x power? Well, you're going to have 1 like this. Again, it's still going to go through 1, but let's see if I can draw this. It's going to be much steeper. Okay, so you see the general shape is the same because these are just numbers greater than 1. Okay, and we know the general shape of a graph like that. But definitely, the bigger the number here is that you're multiplying by, the steeper it is. Okay, so relatively speaking, this one is shallower than this one. If you had 1 million to the x power, it would be like be almost straight up. Okay. Okay, let's move on and look at something similar. What if you had f of x equals 3 to the negative x? Which another way of writing that is 1 over 3 to the x. Or another way to write that is just 1/3 x. So if somebody says, graph this for me, well, you can write this as 1 over 3x, and you can also write this as 1/3 to the x, because 1 to the x power is just 1. 1 to the anything power is just 1, because you're just multiplying it by 1. 1 times 1 times 1 times 1, it just equals 1. And 3 to the x is 3 to the x, so you're left with that. So notice that this is a number greater than 0, but less than 1. Okay? So it falls in that different range where things kind of get backwards. We already looked at that briefly, and we said that it's going to go down pretty much like this. It's going to be kind of the mirror image of the other one. Okay? Because it's between 0 and 1. Okay? And what if you had f of x equals negative 2 raised to the x power? Well, I'm going to draw something that's not necessary really, but it's going to help you out. Here's x, here's f of x. What would the graph 2 to the x look like? We've been talking about that all day long. 2 to the x is going to look like this. That's what this is. But they didn't ask for that. They asked for the graph of negative 2 to the x. Well, if you think about it, every number I put in for x, okay, in this equation, all I do is I slap a negative sign on it. Okay? So really, what it's going to look like is the exact mirror image, because I've taken the graph without the negative sign, and all I'm doing here is every number that I would have had here, I just stick a negative on it, so it just pops down to the negative axis, and that's why it's a mirror image. So what I'm trying to show you here is sometimes you can use plots that you know to find plots that you may not know. What if you had f of x equals 2 to the 3 minus x? And they said graph that. Well, the first thing I would do is I would split this up as 2 to the third times 2 to the negative x. You notice you can do that because it's the same base. You would be adding these exponents, and that's where you started. Okay. Next thing I would notice is that 2 to the 3 is just simply 8. 2 times 2 is 4. 4 times 2 is 8. Okay. And then this can be written as 1 over 2x because you have a negative exponent. So then in the end, this would be 8 over 2 to the x power. Okay? So how would you graph that? This is f of x, this is x. Okay? How would you graph that? Well, let me just ask you, what would the problem look like if it were just simply f of x equals 1 over 2x? What would the graph look like then? Well, then you know, if here's 1, that you would be able to write this as 1/2 to the x, and this number is between 0 and 1, so you know this graph would go like this, right? Through the number 1. But really what I have here is I have that graph multiplied by 8, because I've got an 8 on the top. So it's going to look very similar to that, except let's pretend this is 8 up here. It would go something more like this. It would go through 8 instead of going through 1, because what I have here is I have 1/2 to the x power as a graph, and I'm multiplying that by 8. So here the point was at 1, and I had to multiply by 8, so the whole graph kind of scoots up. And keep in mind, these are qualitative graphs. I mean, they're not really exact, because I'm not taking the time to plot all the points. I'm just trying to give you a feel for the general shape of them as we go. Finally, the final thing I want to do here is point out a very special case of exponential functions. Recall that we've been talking about f of x equals a to the power of x. Now, if a equals a very special number, which is roughly 2.71 dot 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 dot, then we say a is equal to what we call e, and then f of x is just going to be equal to e to the x. Okay? Now you may go, what the heck is this? All I'm really trying to say here is, in nature there are special numbers. They pop up every now and then. One of them is called pi. I know you've seen that. That's a big long number. It goes on forever. There's also a number called e, which is actually just as important as pi. It's just not so known to the general public in everyday use. Okay? The number is roughly equal to 2.71, but it also goes on to infinity. E shows up in exponentials all the time. In fact, it is called the exponential base. Okay? So a very special exponential equation is this one here, where we have e to the x. But just remember, e is just a number, just like pi. It's just a very special number. Okay? So if I had to just kind of draw a comparison, what I would draw would be, here's f of x equals a to the x power, just like what we've been drawing all day. Here's the number 1. Okay? If I were plotting 2 to the x, it might be something like this. It might be a graph like this, right? If I were plotting e to the x, it might look something like this, e being 2.7. And if I were plotting, just for comparison purposes, if I were plotting f of x equals 10 to the x, it would be steeper still. So all I'm trying to point out to you here is that e to the x is just another exponential function like, and I made a mistake here, this is 2 to the x power. Another exponential function like 2 to the x or 10 to the x, okay? But it's just kind of in the middle here. It's just a different graph with a different number as a base. You will almost always, in your study of trig, precalculus, etc., be dealing with exponentials that are involving e. So e to the x is going to be a very common thing you'll be seeing over and over and over again. And that concludes our summary of exponential functions.